Here is the question. How do you get a constant electric field? So the answer is that if you have two parallel plates with equal and opposite charges on them, and they're close together, they have to be close together, then the electric field in the middle is fairly constant, and it has electric field has a magnitude of charge, or that's a charge on one side, over the area of 1 times epsilon naught, where 1 over 4 pi epsilon naught equals 9 times 10 to the ninth newtons meters squared per coulomb squared. So how do you know this? How can you show this? I mean, it's an important thing because we like constant electric fields because they make everything easier. So, but how do you show that this is indeed true? Well, there are a couple of ways. One is to use calculus and do some integration. You can integrate you can integrate over the charge distribution to find an electric field. Another is you could use Gauss's law to find an electric field. But if you're in an algebra-based physics course, neither of those two things work. Now, some people do Gauss's law in introductory physics, but I think it's really a bit of a stretch. So I'm going to show that this is indeed true by building a model. So here's what I'm going to do. Imagine that I replaced my plates. Here's the two plates. And let's say I have just a finite number of charges. Let's say I have 3 charges right here and 3 charges right there. And really this should be in 3 dimensions. How could I calculate the electric field at this point? Well, let's label these 1, 2, 3, 4, 5, 6. Well, the electric field at this point is going to be electric field due to 1, which is like this. The electric field due to 2, it's bigger. Electric field due to 3. Electric field due to 4, it's going to be towards that, right, because it's a negative charge. Electric field due to 5 and 6. And so if I add up all these electric fields, it will be mostly that way. So E equals the sum over I of EI, right? Where I is the index. I can add all these up. So I'm going to do that, right? I'm going to do this numerically. So we need to do that by breaking it into a whole bunch of pieces. And I can have, if I use a program, I can put as many pieces on here as I want. So there's a couple things that I need to do. Let's say I have I have 1 charge. Because if I can do it for 1 charge, if I can tell a computer how to do it for 1 charge, I can tell it how to do it for 1,000 charges. So let's say that this is the XY plane, and then I have a charge right here. I can't put it at the origin because it can't all be at the origin. And here is my location where I want to find the electric field. So let's call that RO, and let's call this RQ. It's the location of the charge. The first thing I need to do is find this vector, R. So I can say R equals RO minus RQ. That's my vector R, right? Because if I take final minus initial, the final position is the observation location. The initial position is the charge, which I know the location, that's RQ. So then the vector R from the charge to observation location is just the difference. Then I can use this, E equals K, where K, this is equal to K. K times Q, I guess we call it lowercase q, over the magnitude of R squared times the unit vector R hat. So that's important, right? Because I need the vector value of the electric field. I can't just use KQ over R squared. I have to use KQ over R squared times this unit vector R hat, which is in the direction of Q. Of R, I'm sorry. And then if Q is positive, it's in the direction. If Q is negative, it's in the opposite direction. But that's it. I can do that for that 1 charge. If I can do it for 1 charge, I can do it for many charges. So how are we going to put these charges in space so that they can represent parallel plates? This is what I'm going to do. I'm going to use a Monte Carlo method. So here's my plates. I need to have actual size. Let's say these are, they're squares. Where L equals 0. I'm trying to think like that big. Let's say they're 10 centimeter long, 0.1 meters. So the area would be L squared. And then this distance S between them, let's say S is equal to, let's Let's try a centimeter. I think that might work. And then how much charge I put on there, let's put, let's say 100 nanocoulombs. I'm just making up stuff here. So that's going to be the plus on this side, 100 nanocoulombs, and the minus on this side. That's the total charge. So the first thing I need to say is how many pieces do I want? What's N? And let's go with N is 500 on each side. So now I can find the charge of each of these pieces. dq is going to be q over N. If I put this as the origin, then I can say all these pieces, I'm going to randomly generate the vector location of these pieces. So the vector location RQ is going to be equal to, the x coordinate is going to be negative s over 2, right? Because I want that to be set. The y coordinate is going to be a random number. The z coordinate is going to be a random number between negative 0.1 and 0.1. So let's stay in the L. Okay, and we can do that in Python. So I can generate a random number. I can pick my observation location. Let's start with RO at the vector 0, 0, 0, but I'm going to change that. And then I will go through, I'll make all my points, and I'll add them to a list, and then I'll go through the list and find the electric field at that point. I'll do that for both sides. Okay, so I'm going to have to use some things like, I'm going to use GlowScript, I'm going to use lists, I'm going to use some loops. So if there's things in here that you haven't seen before, I think you better follow through, but let's just get right to it. And I'm doing this from scratch, right? So there could be some, let's say, errors, but the errors are part of the fun. Let's make this a little bit bigger. Everyone likes it bigger on the sun. A little bit bigger. Okay, bigger. That's good. Okay, let's start off here with k equals 9 times 10 to the 9th. Let's say L equals 0.1, A equals L squared, S equals 0.01, Q equals, what did I say? 100 nanocoulombs. Oh, and then N equals 500. That way, there are 500 charges on each side. And then dq is going to be q over N. Okay, so let's just start and make, I want to make, let's save this. Constant electric field Monte Carlo. I don't know why I didn't save until I run it. There it goes. Okay. So now let's just make these points. So I'm going to say N equals 0. So that N equals 0 is my counter. And there's better ways to do this, but I like this way because it's easy for people to accept in their head. So I'm going to start off at N equals 0. I'm going to increase that until I get to N equals 500. And I didn't put someone once complained about the spacing on my equations. So let's just say while N is less than N, do the following. Number 1 is I need to generate a random location on the positive plate, which is on the left. So I'm going to say R temp, it's a temporary vector. The x coordinate is going to be s over 2. The y coordinate is going to be equal to L times 2. Let's see, it's going to be L times, 2 times random. So random returns a number between 0 and 1. So I multiply by 2, right? And then I'm going to subtract 1. And here. So that's going to, 2 random minus 1 is going to give me a number between, the maximum it can be as random as 1, and I get 0. Was that right? No, I get 1. Right? If random is 1, I get 2 times 1 minus 1 is 2. If random is 0, I get 0 minus 1. So this inside this right here goes from -1 to 1, and then I multiply it by L, so give me the size of the plate. Now I just need to do the same thing for the z component. That's my vector. Okay, now, up here, let's say this. Left equals, this is my left plate. It's an empty list. And now I'm going to add to that left plate an object. So let's say left equals left plus an object that's a sphere. Its position is going to be the vector r temp. Its size, let's say, if the separation is, let's try 0.001. That might be too small. And let's also give it some other properties like dq, right? That way I can reference the charge. Actually, let's just call it q, lowercase q. That's the charge of that sphere. Q equals dq. Yeah. Okay, now I need to increase my n value. N equals n plus 1. Now let's go ahead and save this and run it, because this should just make 500 points in a plate that we can use. Let's run it. Nothing happened. Left plus sphere. Left, I think. So maybe I missed a sign up here. No, that's right. So vector that. See? That. Okay, that's right. So left equals a sphere, r temp. Oh, equals. No, that's fine. Oh, I didn't put the equal for size. And it should be radius. I was thinking about the size when I typed that, and I didn't actually type it. Okay, there's my plate. That looks pretty good. Okay, there's my 500 charges. Okay, now we need to make the other plate. So I'm going to go over here, and I'm going to say right equals an empty list. And now I'm just going to copy this stuff. I need to reset n, so I'm going to say n equals 0. And then I'm going to do the same thing, except, oh, this should be s is minus s, the x is minus s over 2, and that's s over 2. And then the charge is going to be negative dq. And let's run. We can make it a different color, just so you can see. So let's make this top one blue and red and yellow. Let's do red and yellow. That'd be fun. So up here, I'm going to say color equals color dot yellow dot red, right? The positive is red, negative is, let's make it cyan. I don't know what I'm doing here. Color equals color dot cyan. Aha. There's my charge plate. Look at that. Oh, that's cool. Look, it's like a run on the Death Star. I'm zooming right in between the. I want to play that more. Okay, stop. So there's my 2 plates. Now I need to calculate the electric field. So let's just go ahead and say RO is my observation location, and I said I wanted that at the origin. And then I'm going to calculate the electric field at RO. Okay, so let's say let's do this. E equals vector 0, 0, 0. So I'm going to calculate the electric field due to each charge and add it to that, right? And then so I need to start with some 0 value, and then I can add to it. So now I'm going to say while, let's do this, for QQ in left. So this for loop says QQ is actually one of the objects in there, right? I didn't want to use Q because Q is a parameter. I think it would work. But QQ is a temporary charge. Actually, QT for temporary Q. Yeah, that looks better. So it's going to go through in each one of those, and I can reference it. So now I can say DE. Now, the first thing I need to do is find R. So R equals RO minus qt.pos, right? Because qt.pos is the vector location of that charge. So RO minus RQ, that's really RQ, that gives me the vector R. Now I can use that to calculate the electric field. DE equals K times qt.q, that's the charge, times norm R. Norm returns a unit vector in the same direction as R. And then I can divide by mag R squared. So mag R is a built-in function in GlowScript v Python. I am using GlowScript v Python. I don't know if I said that, but it may be obvious. And this allows me to have these functions like sphere and vectors and stuff like that. You could do it other ways too. But so mag r returns the magnitude of r, and that's my electric field due to that one piece. Now all I need to do is to add that. So E equals E plus dE. Now I've added it to there. That's it. Once I do that, I've gone through that whole 500 piece thing on the left and added it to the electric field. Now I need to do it for the other plate. So let's do this. Copy. Paste. For QT and write. So, I mean, I probably could have I could have had one list called charges, and it would be both plates. I don't know why I have two separate things. Sometimes you don't think things through. You just go with the moment, right? But still, there's my electric field right there. So let's go. That should be done. Now I can print E calc equals E Newton per Coulomb. Now let's also calculate the theoretical value. So ET is going to be equal to I'm just going to calculate the magnitude. It would be, what was it? Q over A times epsilon. So epsilon is 1 over 4 pi times 9 times 10 to the 9th. Is that right? Wait, so at 1 over 4 pi epsilon naught equals 9 times 10 to the 9th. So if I solve that, I get multiply epsilon naught. Yeah, so let's write this out right here. So let's call it E0, ep 0, equals, what did it say? 1 divided by 4 times pi times 9 times 10 to the 9th. I think that's right. So E calc is going to be equal to, did I already start typing that? Yeah, I did. ET for theoretical, divided by EP0. And let's print that. And that's going to be a scalar, but that's fine. Okay, if this runs without an error, I'm going to be super impressed and surprised at the same time. I guess I should technically save it. Now I should run it. Okay, no errors. The theoretical is 1 times 10 to the 6th. I got 2 times 10 to the 5th. And I have a significant, it's 10 times less y component and z component. Let's just run it again because it's a random thing. Okay, let's increase in. It's obviously not having a problem with 500. So let's do 1,000. Still not work. That's still not that many charges. I think we need more charges. 10,000 charges. Oh, it's like, oh, I don't know about that. Okay. I'm still off by, I'm like at, it should be something like 1, and I'm at 0.2. Negative DQ. Oh, right. I didn't change this. I didn't change. I added it to the right one, which is fine. I don't think this changes anything. I did have them all in one list. But that should be negative. Okay, let's just... Okay, so now the y value is very low. What if I put the plates closer together? So I can just change this to 0.05, half the distance. Why is this not working? I thought it would work better. Well, let's try this. Let me move my location. I keep getting around 2.4 times 10 to the 5th. I'm going to move my location a little bit off the axis. I can do that by just putting this at 0.001. What was S? 0.005. So that should work. So now it's let's see if I still get something. Okay, so I'm getting a constant electric field. I feel like I'm calculating the theoretical electric field wrong. Q over A epsilon naught. That is the electric field due to a constant. Q over A. I just think it should be a lot better than this. Okay. I'm not sure what to do now. I think I'll just stop here. And I think I did show that. Let's move this up in the y direction. So let's move it up 0.005. And I should still get fairly close to the same value. I am. That is still close to the same value. And I'm just surprised that it looks like a constant electric field, but it's not the same as before. E electric is Q over A divided by epsilon naught. And A was L times L. I wonder if the size of my plate's the wrong size. But okay, I think I've shown that the electric field is constant and there is some issue. But I want to make a graph of the electric field as a function of position between them. However, in order to do that, I have to build a function. And I already have a long video. I can do it anyway. What does it matter? Let's do it. Okay, let's make this a function. Okay, so I'm going to say def E. And I'm going to give it t left and t right and RO. So I'm going to pass to it the two lists, the left and the right. And those are lists of charges. And then I'm going to just calculate the electric field. So I can just tab indent this. Tab indent this, and I'm going to say this is t left, not left. R equals RO minus QT dot. That's fine. This is fine. This is fine. Oh, I can't call that E. So let's call this ET. Because I can't have a function in a function name the same thing. I think you can technically. Okay, and then over here there's going to be T right. And I need to indent this. That's indented. That's indented. That's indented. And call this T. T. And then I'm going to return the vector ET. Okay, let's just try this. E with left, right, RO. And I should get about the same thing. It won't be exactly the same thing because it's random. So 2.6 times 10 to the 5th. Okay, 2 points. It changed a lot. Okay, but that's fine. I'm happy with that. Okay, now we can make a graph. I can redo this. I actually need to take this down a notch. So let's have half the number of data points because I don't want to go crazy. So now let's make a graph. So let's go down here. G1 equals graph. And let's leave off the top title. X title is going to be equal to position. Let's just say X in meters. And the Y is going to be EX in volts per meter or newtons per coulomb, whatever makes you happy. So I can't plot the electric field. I can only plot a component of the electric field. So now let's go over here. F1 equals G curve. Color equals color dot blue. And now I'm going to collect data. So let's say x equals negative 0.9 times s over 2. That's where I'm going to start. That's my starting x value. I don't want to start right at the plate because it'll be too, if I'm on the plate, bad things can happen. So I'm going to start a little bit shorter. And now dx is going to be s divided by 20. So I'm going to have 20 steps across, mostly. Now I can say while x is less than 0.9 times s over 2. Right? I'm going to go until it's up that other plate, 0.9 of the way. Step 1 is to set my location of my thing. So I'm going to say, I guess I should do it up here. So say RTO equals vector x 0, 0. And then I will say, I can do this all in one stop. f1.plot. I need to pass it the left, the right, and the vector location of the observation location, which is RTO in this case. And then that's my, I left off some stuff. That's E plot. E of that dot x. That E and all that stuff is a vector. That's what's returning. So I can just say dot x. That is the x component of that returned thing. And that will be versus, I'm sorry, I want that x versus that. So it's going to be, let's do this. RTO dot x, RTO dot x. Okay. Now I need to increase RTO. So RTO equals RTO plus vector dx 0, 0. Okay, let's see if this thing runs. Okay. So it did. And I got a changing x component. It went from as high as, what's that, 4 times 10 to the 5th, and as low as 3 times 10 to the 5th. But then, that's fairly constant. I'm pretty happy with that. Actually, you can't even see this whole thing. I made it too big. So that's pretty good. Okay. I think I could do this better, but I think it's a good introduction, and I had fun doing it, and I appreciate your accompanying me on this journey of calculation. I will indeed give you the code down below, and I hope that you have a good time.